Hi and welcome to the first podcast in this part of the course about type functional programming in Haskell. In this podcast, I will introduce some of the basic notions in Haskell and in type functional programming, and I'll also talk a bit about the history of type functional programming. Before I get around to all that, let's have a look at the learning goals of this session. There are several related learning goals in this session. The overall goal is that you should be able to start thinking about why type functional programming is important, because it really is important. Next, another goal is that you should be able to install and run Haskell, because you'll need that for the remainder of the sessions. And you should understand the general structure of a Haskell program. You should understand the simple expressions in Haskell and their types, because it's crucial to remember that everything in Haskell has a type. You should be able to define recursive functions over simple data types, and be able to define simple functions over lists, and be able to use anonymous functions. And finally, because this is about type functional programming, you should be able to informally find the types of simple expressions, including the types of functions, and to understand the role of types. So, why is type functional programming there in the first place? Well, the subject has a history that goes back to 1936, when Alonzo Church, the American logician and philosopher, developed the lambda calculus as a fundamental model of computation. Around the same time, Alan Turing developed the Turing machine, which is of course a very different model of computation. But when Alan Turing was to do his PhD in the United States and went to the United States, he met Alonzo Church, and Alonzo Church became a supervisor. So some of the first work on type lambda calculus is due to Alonzo Church, but also to Alan Turing, and to Haskell Curry, who was one of Alonzo Church's other students. The work on being able to evaluate lambda expressions on a computer actually begins in 1948, and is the work of one of Alan Turing's students, in fact his only student, Audrey Bates. And she worked on evaluating lambda expressions on the Manchester computer at Manchester University. The next step along that line in turning the lambda calculus into a programming language is the work on Lisp by John McCarthy. And after that, another important step is the emergence of the so-called SECD machine, which is due to the English computer scientist Peter Landin. We've got him here. The notion of lazy evaluation, which you can find in Lisp-like languages but is also prominently important in Haskell. The notion of lazy evaluation is due to the English logician and computer scientist Christopher Wadsworth, and that goes back to 1971. Now, where does the history of types in functional programming begin? Well, of course it begins with the type lambda calculus, but its introduction into the world of programming languages begins in 1972 with the emergence of the polymorphic lambda calculus, which is a very rich type system for the lambda calculus, and it was discovered independently by the French logician Jean-Yves Girard and by the American computer scientist John Reynolds. Now, this is Girard, this is Reynolds, but the really important figure here, or the important figures here, are probably Roger Hindley and Robin Milner, because in 1977 it was discovered that there is an interesting fragment of the polymorphic lambda calculus which can be used to give a type system for the ML language. And Robin Milner came up with that, and at the same time Roger Hindley, who is a Welsh logician, was working on the exact same type system independently of Robin Milner. And what's important and what's great about this version of parametric polymorphism that you find in standard ML and also in Haskell is that it allows for type inference, so you can infer types of expressions automatically, and the type system is still very rich. So standard ML is, in essence, the first type functional programming language around, and it's still around. After standard ML came other dialects, such as OCaml and much later F#. The next important type functional programming language is Miranda, due to David Turner from the University of Kent. Miranda has many of the features that you find in Haskell, such as lazy evaluation and type system, which is very similar to the type system for standard ML. After that, Haskell slowly emerges. Monads, which are central to Haskell, were developed by Eugenio Moggi at the University of Edinburgh. I was there when he gave his first lecture on monads. Philip Watler and many others. And from around 1990, all the various similar lazy functional programming languages, including Miranda, gel into a single lazy, strongly typed functional programming language, which is Haskell. And this is where the story of Haskell begins. And it built on all of its predecessors, on the work of Alonzo Church, Haskell Curry, Alan Turing, on the work of John McCarthy, Peter Landin, Christopher Wadsworth, and the work on type inference by Hindley and Milner, and the work by David Turner. So Haskell really is yet another milestone in this history. But the burning question is, why bother? The big question is, of course, why would you want to use typed functional programming? There are some very good reasons for that. One is that types lead to readability. If you annotate your program with types, then the program can become more readable, much more readable. But of course, that's not the reason why you want to use type functional programming specifically, because this was a reason that would apply to any programming language with a notion of types. A much deeper reason why you want to have types in a functional programming setting is that types are in fact program specifications. A type specifies a program property, and the reason why that's the case is that in this case a type is in fact a logical formula. It is not something that we will have time to spend a great deal of time on, but in a functional setting, types are in fact logical formulae, so types allow us to specify program properties. Thirdly, type programs cannot go wrong. More precisely, what that means is that if a program is well typed, then certain runtime errors will not happen. So a well-typed program actually guarantees a lot about the behavior of a program. This also means something for the program process. More precisely, what it means is that programming is different. In an untyped setting, or a weakly typed setting, such as Python or C, what happens is that you can very easily, or well, comparatively easily, build a program. You can build a running program, but then you spend time testing and debugging. But in a strongly typed setting, and when I say strongly typed, I mean in the sense of Haskell or ML, it is not so easy build a well-typed program, but once your program is well-typed, a lot less time is spent on testing and debugging. So the focus shifts from testing and debugging to making sure that your program is well typed. The programming process is different, but the advantage of this is that well-typed programs can't go wrong. So you get a lot out of this effort that goes into building a well-typed program, because a well-typed program can't go wrong. So that's a very deep reason for wanting to have a very strongly typed functional programming language around. In languages such as Haskell and ML, you have type inference. So in fact, you do not need to write types at all. In fact, types can be left implicit. But it's often useful to write them anyway. And in this course, we're going to write types anyway. Because that way, when we write types, we're actually writing a specification of the program. So we can write the types into our program if we want to, but we don't have to. And sometimes when we're more experienced, we don't always write down the types in our program. So type inference also means that programming can be a bit different, or very different, from what you see in an untyped or weakly typed setting.